When I tell people that I'm a mathematician, guess what is the most common response I get? I'm not good at math. And to me, this is like talking to somebody who has learned music scripts in great detail, but never actually listened to the music. It's not that everybody should love mathematics or enjoy mathematics, but in many cases, many people never got a chance to actually experience mathematics, to actually decide for themselves if they like it or not. Now, I would like to think of Avengers movies. Most of you have probably seen Avengers movies, and you may or may not have your favorite character. I definitely have one, and my favorite character is Tony Stark, the Iron Man. For this reason. Think about how he goes about new scientific inventions, his engineering projects, and so on. He has this 3D display, and then he manipulates a bunch of stuff with his hands, and then he comes up with a new idea or a new invention. This is how I do math. This is the most accurate representation of my research process that I have ever seen on screen. It's just that I don't quite have that equipment yet. This happens in my mind or on my computer screen after doing a lot of coding, rendering, and so on, visualization. Now, before I move on to other things, let me just tell you a little bit more about myself and my field. So I work in mathematical optimization. Mathematical optimization is all about taking a practical problem, converting it into a mathematical form, which we call modeling, and then finding the best method to solve that mathematical formulation of that problem. You can think about some practical optimization problems like facility location. So a company wants to put a warehouse somewhere and deciding on the best location to minimize the transportation costs. You may think about a tech company producing a new line of mobile devices and then deciding on best prices to maximize the revenue and so on. Now, when we think about an optimization problem, this model or mathematical formulation, we make decisions, we make choices. So, for example, we choose the prices for different devices. And those quantities, they are our variables. We can represent them as coordinates of points in space. So we can think about some region in space called a feasible region, where all those variables live. From this region, we choose the best possible combination of those values, the best possible point. That will maximize or minimize our objective function. So let me show you one feasible region. It's an example of a feasible region for a very common, very modern kind of optimization problem or optimization model called semi-definite programming. So what you see here mathematically is actually a three-dimensional slice of a six-dimensional object, which is a standard object that is called a cone of positive semi-definite matrices. And it's actually written in this first equation there. Now, if you look at the second bunch of equations, you can actually see them in a picture. So if you look at this picture, you see a lot of structure for that problem or for that feasible region, right? You see that the boundary of that object is part of a larger surface that we actually call an algebraic variety. And you see that this object is cut out by those planes. So by looking at this picture, most of you have learned much more about this class of problems, semi-definite programming problems, than you would if you just looked at the equations. Even if you're a mathematician, maybe not familiar with this area, that would still apply to you. And I would like to talk a little bit about my own research. So I have to say that maybe 10 minutes is not enough to explain all the details to you, but I didn't want to cheat, right? I wanted to show you something that I'm actually working on. So I hope that I will be able to explain the intuition, to just show you how this works, how visualization and intuition helps me to solve mathematical problems. So in this particular problem, we were looking at two different properties of feasible regions or convex objects. One property is easy to see. It's called facial exposure. So if a person in my area looks at this object, they will see this object is facially exposed. Another property is very difficult to check. It's called niceness or facial dual completeness. And we thought that those two properties are the same. So my goal was to either prove this result or to find a counterexample, and I ended up with a counterexample. So in fact, this object is a three-dimensional slice of a four-dimensional cone that satisfies one property, but not the other. I can see from this picture that it satisfies the first property. Then I can look at the dual object, and again, I can see that the second property is broken. So I can see it's a counterexample. How I do it? Well, I look at this tip here, and I see that there's this curve coming out of this tip, and I see, because I know how the property works, that it breaks my property. Now, what I want to tell you about this is that when I was working at this project, I could come up with different examples, different ideas, immediately see this dual object. And once I noticed there's this curve, that specific structure, I knew that I have solved the problem. I knew it was a counterexample. So it took a while to write down the formal proof. Then I had to publish a paper in a journal, go through peer review process, and so on. But at this stage, if I showed this object to any person working in my field, and especially anybody working on that particular problem, because a lot of people were interested in it, they would immediately see that that's a solution. That's a counterexample. This is like hearing the music. This is what experience mathematics is like. Now, not all mathematics can be visualized. But most mathematics that I do and most mathematics that I teach can be. The problem is that it takes so much time, and they have put so much effort into doing this, that mathematicians have learned different techniques to do all those things in their minds. So we read mathematics from formulas, we communicate mathematics in plain English, and we have this scaffolding, this interface that allows us to build this intuition, to build those pictures in our minds. However, these days, it's becoming easier and easier to visualize things. And if you look at this picture, it wasn't all that difficult to produce. 10 years ago, it would be possible, but very hard. 20 years ago, I wouldn't even think about producing an image like this. The equipment that will be available for us to do mathematics in the future will be so advanced that it's probably even difficult to imagine now. What will be available in 70 years? Professional mathematicians will be able to do mathematics in an intuitive way, bypassing a lot of technical computations. The tools that are available, that will be available to professional mathematicians, will be also used by everybody. So everybody will be able to enjoy mathematics in the same way as these days we can all enjoy art, history, and other fields of human endeavor, even if we're not professionals. In 70 years from now, if we haven't destroyed the planet by then, everybody will be a mathematician.